Problem number 9, let I be the integral from 0 to 1 of sine of 3x divided by x dx. So part A is that we have to find a convergent series whose value is I. So how are we going to do this? Here's our game plan. We know a Taylor series for sine of x. We're going to substitute in 3x into that Taylor series to come up with our Taylor series for sine of 3x. We'll divide term by term to bring in this dividing by x. And then we're going to be allowed to interchange the order of the integral and in our series. So let's start working this out. Okay, so first thing that we're going to write is sine of x is the sum from n from 0 to infinity of minus 1 to the n divided by 2n plus 1 factorial, and it's x to the 2n plus 1 power. Okay, now what we're going to do is replace x with, nope, not 2x, but 3x here. And that will change over there. So we end up with sine of 3x is sum of n from 0 to infinity minus 1 to the n, 3x to the 2n plus 1 divided by 2n plus 1 factorial. Okay, at this point then, I'm going to divide everything by x here. And so what effect is that going to have? Well, sine of 3x divided by x is going to equal the sum n from 0 to infinity of minus 1 to the n divided by 2n plus 1 factorial. I'm going to split this chunk up. 3x to the 2n plus 1 is going to be 3 to the 2n plus 1 times x to the 2n plus 1. But when we have x to the 2n plus 1, and then we divide by x, that's subtracting 1 from the exponent of x. And so this would be x to the 2n. So this is, step 1 is coming up with our Taylor series, our Maclaurin series, in fact, for sine of 3x divided by x. Okay, step 2 is we need to integrate. And so here's the thing, that if I just put on, let me use a new color here, the integral from 0 to 1 of this dx, I can just slap that on as well. But realize that a lot of this doesn't have anything to do with integration by x. So I can highlight right here everything that I just put inside this blue box. It doesn't have anything to do with x. I can interchange the order of the integral with respect to x and the sum with respect to n, and I can move all of these n terms outside the integral with respect to x. And so when I do that, I end up with I is the equal to the sum from n from 0 to infinity of minus 1 to the n times 3 to the 2n plus 1 divided by 2n plus 1 factorial. And now I write down the integral here from 0 to 1 of x to the 2n dx. So the only thing left over here in terms of x were the integral from 0 to 1 of x to the 2n dx. Okay, so now it's time to evaluate this integral. I'm going to stop writing this for a little bit just to evaluate this integral right here. So we add 1 to the exponent of 2n to get x to the 2n plus 1, but then we have to divide by that exponent. We're going to plug in 1 and 0 respectively, and we end up with 1 to the 2n plus 1. It's just 1 divided by 2n plus 1. And multiply that, not multiply, but subtract 0 to 2n plus 1 divided by 2n plus 1, so that's just 0. So putting everything together here, our integral I evaluates to the sum from n from 0 to infinity of minus 1 to the n times 3 to the 2n plus 1 divided by 2n plus 1 factorial times 1 over 2n plus 1. And this is our final answer to part A. We have a convergent series whose value is I. Okay, now for part B, it says how many terms of your power series must you keep to guarantee that your truncated sum approximates I with an error of, at most, 10 to the minus 2. Okay, what do we do here? Well, let's start writing out the first several terms of this series. So when n is equal to 0, we end up with 3. Minus 1 to the 0 is just 1. 3 to the 2 times 0 plus 1 is just 3 to the 1. 2 times 0 plus 1, that's 1 factorial, and then divide by 1. So this just ends up as 3. When n is equal to 1, minus 1 to the n is minus 1, so I have a minus sign. 3 to the, well, let's just say here, 2n plus 1, when n is 1, will be 3. So I have 3 cubed divided by 3 down here times 3 factorial. When n is 2, minus 1 squared will be a plus sign. When n is 2, 2n plus 1 is 5. So I have 3 to the 5th divided by 5 factorial and an extra 5 there. When n is 3, we'll end up with 3 to the 7th divided by 7 times 7 factorial. When n is 9, we'll be back to a plus sign. 3 to the 9th, sorry, when n is 4, 2n plus 1 is 9. That's what n was 3 right there. 9 times 9 factorial. So those are the first 1, 2, 3, 4, 5 terms. Now if you punch all this stuff into a calculator, what do you end up with? 3 minus 3 halves. I'm doing lots of simplification here. I wrote this out ahead of time. Plus 81 divided by 200 minus 243 divided by 3920 plus 27 divided by 4480 minus dot dot dot. Okay, so these are the first several terms here. Something we should realize here is that we have an alternating sum. We have an alternating sum here, an alternating series, minus 1 to the n. And not only that, but by the alternating series test, we can quickly see that this is going to converge. And the terms are decreasing in absolute value and going to 0. So alternating series test is going to tell us that this converges. But to answer the question about an error, we want to bring back this corollary here to our alternating series test, which, let's just jump straight down here. When we approximate s by s sub n, so a partial sum here, the error is less than b sub n plus 1, the first omitted term. And so we're looking for an error of less than 10 to the minus 2, less than 1 in 100. And so this term here is less than 1 over 100. And so if we approximate s by the first 4 terms here, the error is less than the first omitted term, which is less than 1 over 100. So how many terms do we need? We need these 4 terms, the terms for when n runs from 0 to 3. We're guaranteed to know that our truncated sum for these 4 terms were within 1 in 100 of the actual answer.